Welcome, and so in the last class and the lab you had seen how to use down stacked autoencoders, and the idea was that if we have a large network and in order to get around with the complexities with training down the weights and then the total complexity associated with the dynamics of the free space of weights, then can we have a simple way of doing it out. So, following that is something which is called as denoising and sparse autoencoders, and where this comes down to play is that denoising autoencoder, as the name suggests, is that it can have a major use in terms of denoising or removing out noise from patches or examples over there, and sparse autoencoders are where you would be making use of sparsity theory. Now, these two are very important in two different aspects. One is in order to prevent something which is called as memorizing of examples by a network, or an overfitting scenario, in which what typically happens is the network would tend to learn examples and memorize them. Instead of trying to learn down patterns, it would be memorizing the examples itself. So, within an autoencoder, since your basic job is basically whatever is the input you given, you are supposed to predict down the same as the output over there. Now, you would try to make the network not memorize these things, but rather to actually represent it in terms of features, and then that's the basic idea of learning. Even for human learning, I mean, one way is that a lot of people just memorize and then they go and just write down in an exam and then they forget it out, but that's not what is the essence of even human education or human learning. So societal learning is where you would try to grab an essence and then develop your intellectual potential, which is your own neurons in your brain. They are supposed to fire down appropriately for anything unseen. It should not be that whatever you have seen in the book, anything which comes down in across your life, which is very different from that you will not be able to solve it out. So that's exactly the same way which we try to do with these kind of deep neural networks as well, and that's where denoising and sparsity within autoencoders does come to play. So, without waiting much, let's get into what I would be doing. So, typically what it's arranged as is I would be revising that first basic math of autoencoder once again, and so the reason that I am going through them, sort of a lot of you will be getting down that I'm just showing down the same set of equations and a lot of those slides which look like repeaters, but the main reasoning is so that you can actually learn to relate these salient changes between what was earlier and what we are doing now. So, this what happens from an autoencoder when we go into a denoising autoencoder, and what is the change which happens from going from a denoising autoencoder to a sparse autoencoder, and are there some ways of combining these denoising and sparse factors together. And also you need to keep in mind that actually all of these examples can be extended down to your stacked autoencoder. So, it's not something like if you are stacking it down, then you cannot use these kind of different strategies, because each is a different way of doing it. So, stacking is a way of geometrically building up the network, whereby using lesser and lesser number of resources in order to create a much deeper and complicated network, and denoising autoencoder is a way of basically training down the network and getting a way in which you stop it from memorizing examples. Sparsity in autoencoders is trying to make down redundancies in weights and impose down some sort of redundancy in whatever it's learning. So, each has a different objective and all of them can be combined very much together. So, at the end we will be looking into examples of stacked sparse denoising autoencoders, basically taken down all of them together and what it goes down. So, in the subsequent tutorials using coding which we will be doing, we will be also touching upon all of these examples. So, you will be seeing a repetition of what you had solved with autoencoders and then brought down the stacking concept over there, then also going over denoising and sparsity criteria to find out whether that does work out in terms of your examples as well. And then incrementally we will also be seeing down what we gain by bringing in all of these concepts as well. So, getting started with a very simple autoencoder. So, what you had was that, say at a particular location x, which is a x comma y location within an image, and you take a small patch around that location, and that's what is called as p of x. Now, p of x is going to be a set of pixels which get arranged, linearized and arranged over here. So, for a 5x5 patch from a grayscale image, you have 25 pixels. For a 5x5 patch from a color image and RGB color image, you would be having 75 pixels over here. You have your bias connected over here, and then so in some of my examples you might not be seeing this node as 1 and then this bias connected, but always keep in mind that this is an intrinsic factor. So, if I have just a bus kind of one single arrow which connects down input to my hidden layer, always remember that it's nothing that it's a zero bias network, it's a perfectly valid bias network. So, you have a bias connecting the these like there is always a bias in the connection to the input of the hidden layer as well, and similarly it goes from the hidden layer to the output over here as in this case. So, this is just one single zone of an autoencoder, or as you had looked down in your stacked autoencoder, you remember that it's just with using one hidden layer. So, you had W1 and W1 dashed which you were training down, and then you could do something else. So, we will stick down to only this hidden layer, we are not looking into classification problem as such currently. So, a simple autoencoder is what can be defined mathematically of this form, that the output of say this hidden layer, all the neurons over here is what is the tensor y, and that is basically this is not output of exactly this one, that there should be a nonlinearity as well, but if we consider that nonlinearity is 1, then if the unit transfer nonlinearity, then you can pretty much have it represented in this form. Now, the result of this next layer is what will be coming down into this form in terms of W dashed and B dashed. Okay. Now, your basic learning rule is where you would like to have this particular cost function, which is the difference or the Euclidean norm between your p and p hat for nth number of samples, and summed over all the n number of samples, this needs to be minimized, and that is your basic learning rule which you are going to use within a simple autoencoder. Now, standing on top of that, if I would like to go down with a denoising autoencoder, then let us see what happens over there. So, with the denoising autoencoder, the structure as such remains the same, you do not make any change within the structure. So, that is what I was saying, that if you would like to do a denoising autoencoder on top of a stacked autoencoder. So, stacking is just a way of geometrically building up the network. Denoising has nothing to do and a zero relationship with any of those aspects of stacking down. Now, for a stacked for denoising autoencoder, what happens is, for a simple autoencoder, while you will have this particular kind of a form, for a denoising autoencoder, the difference is that you bring in this extra tensor over here, which is called as R, and this is a noiser or a noisy parameter. So, what we do typically is that I would try to add down a noisy parameter along with my input patch over there, and this noise is what is randomly generated, it is a stochastic generated noise. So, within your learning framework, within what you do is typically you have a set of learning examples, and then on within every epoch you iterate over all of these set of learning examples over there. Now, whatever is the value of p for a given sample number over there, it is going to be the same across all the epochs. So, there is going to be no change over there. But now, if I bring in a random noiser over here, which means this R is going to be a random number which is generated every time you are trying to access some patch over there. So, for the first epoch, whatever is the value of R for a given sample, in the second epoch the value of R is going to be different, and according to that, this p plus R, this combination is also going to be a different value which comes down, and that what it would mean is that around the same sample you are going to draw a certain amount of slight perturbations, and these perturbations are what will be to the network, what it stops the network from doing is it will stop it from memorizing it, because you are not going to see the same written way of example every time, but you are going to get down some different way in which it keeps on coming down. Now, if you have a nonlinearity after that, then this nonlinearity adds, and this is the typical form, and on the output side what you would try to do is you will get down a p hat, but here the output of this y, or the first hidden neuron, that does not get any noise added to it. The noise is just added on the input side of it, and then when I am trying to look into the output over there, my cost function will include just trying to find down the L2 norm between p and p hat. So, here I am no more going to put down p plus r. So, what that necessarily means is that I cannot keep my training data already pre-corrupted onto my data set. So, every time I am trying to access a particular sample from the training data, I will have to introduce my corruption of the noise, this random value, exactly at that point of time. I cannot keep it pre-corrupted at any point of time. Now, this is one part of my cost function which is p and which is made out of p and p hat. Along with that, I also have another part of my cost function. So if you look into it, all of these are equally weighted. So this is 0.5 weight and this is 0.5 weight, which means that there are two parts of a cost function and I am weighing two parts of a cost function equivocally. Now this other part of it, which is just an orthogonalization factor over here, and which is typically used for the factor so that I have maximum amount of dissimilarity between neighboring between the kernels which I am learning. So what W transpose plus W dash transpose W would do is that this would return me a square matrix over here, which is the same size as that of my number of neurons over there in my hidden layer, and then I try to take a trace. Okay. Now my objective is that I would try to minimize this whole cost function. So that would mean that I need to minimize this part of my cost function as well as this part of my cost function. If I want to minimize this part of my cost function, so that would mean that my trace or the diagonal sum over there has to also be minimized, and that means that very strong correlations at any point of time between kernels from one side to the other side, that has to be reduced, or what typically would also mean is that there has to be minimum correlation between W and W dashed. Say one cannot be the inverse of the other. So this will be maximum only when W and W dashed are inverse of each other. That's what comes down from the mathematics over there. So this together as a cost function does restrain me from memorizing samples, and then my total learning rule is what goes down according to this kind of a form, that I would try to minimize my cost function over all of these values of W's and B's together taken. Now this is what qualifies as a typical case of a straightforward denoising autoencoder. Now we did say that we would be touching upon another, which is also called as sparsity. Now for sparsity, what you do is that, say I have a simple autoencoder which can be modeled in this form, and if I put down a nonlinearity, then I have this extra nonlinearities coming down. Now in sparsity, I don't so here I am assuming that this is a denoiser which is already added onto it. So this is a noisy vector which is added, and then I am trying to predict out p hat such that this network can learn to be denoising. But then I would also want that, so this JW over here is what comes down from my previous case of JW. So in my earlier case on my denoising autoencoders, whatever is my cost function, that is known as JW. So I would be using this part of JW, and I would bring it over here in case of my sparsity as well. So this JW part is retained, plus I put down another factor beta times of this scale divergence of rho L. Now this rho L is basically my sparsity coefficient, or this is the probability of getting a non-zero value in these weight matrices over there. So if I have W1 and W1 dashed over there, so what typically means is that all of these are some sort of tensors or matrices over there. A lot of those can be 0 and some of them can be non-zero. So my probability of getting a non-sparse matrix over there is basically the number of elements of this matrix which are non-zero divided by the total number of elements on this matrix. Okay. Now, if I have a target that I want to have 20% of it as my target of non-zero values and everything else as a 0 value, then the scale divergence will be 1 when these two probabilities are almost the same. Okay. Now, if this is like way ahead of it, so it might be a very non-sparse or a highly sparse, but in both the cases the distance will be large, and it will try to impose it to coming down to a particular sparsity level itself, and as in over here it is a 20% sparsity. Now, what I do is that I add this one onto my earlier cost function and then create a new cost function which is called as JSparse, and then my learning algorithm is basically to minimize this JSparse over here through this learning rule, and that is what will impose a sparsity. So while in the earlier case we did look into that so that the inversion problem does not, so that the memorization does not happen within the network, we would try to keep W and W dashed not as invert of each other, and that can be achieved by your trace summation over the trace part of it, and then trying to minimize that total matrix sum. Now, the other part of it is, which is where I would try to have most of these weights as zeros, and the advantage which you get down by putting most of these weights as zeros is that the dot product or multiplication product is going to be 0, and as such the number of values which you get through it are going to be very low valued, not very high values which will just saturate out your complete network. The good thing on top of it is what we had done in the first class on autoencoders, where I was showing you a few of the classical examples. So, in one case where the image was looking very diverse and you had a lot of noisy and randomness features present over there, we did learn out, and that was an OCT image, we did learn out that it is not necessary that a very noisy and randomly appearing image will have a lot many number of unique kernels. So, you did find out less number of unique kernels, and then in the second layer there was a huge amount of sparsity. So, we will be revisiting that example once again over here as well. And now on the other side of it, you did see that when you were looking at retinal images, then over there although the image appeared clean, but the amount of diversity was very high and the system was not at all sparse. So, this sort of a learning algorithm, sparsity, actually imposes that, and there are many more theoretical implications which we will be seeing down in the later on lectures as well. So, let us start just get a revision concept of that one. So, the earlier thing which we had done with a standard MLP problem of a pixel classification was where I take down a patch over here, then train down 2 autoencoders, and here it is a denoising autoencoder. And now that if I train it down by stacking one behind the other, so you can very much call this as a stacked denoising autoencoder. So, your denoising criteria is applied, and now if I apply down a sparsity criteria as well, then I can call this as a stacked denoising sparse autoencoder. And accordingly, I take down a patch over here, and then I keep on moving it pixel by pixel, and that will give me a raster movement, and based on that raster movement I would be getting down each pixel classification, which is collated to form this matrix of my classified tissue map coming down over here. Now, where it goes down is that my noisy factor is what is added down to my input over here, and even in my final training also I would be having that noisy part added, and then the final cost function after the autoencoder training is over is something which will no more make use of other factors, but it will just be making use of this factor of L2 norm between my predicted class, which is my Tm, and my actual class in my ground truth, which is omega m. So, that was a pretty straightforward thing which we had done in the earlier one, but here we are just introducing the concept of sparsity, denoising, as well as the stacking way of learning it down with lesser number of weights. Now, so let us get into this revision of that handwritten digit recognition. So, remember that in the last class we did say about this particular problem. So, this was about trying to recognize handwritten digits, and that is a 10 class classification. So, you need to understand which numeral is it from 0 to 9, and so you basically have 28 cross 28 pixel sized patches over here, and everything is integer valued 8-bit number, although they are binary images, which means that the gray area over here, the background is 0, and whatever is white has a value of 255. And for training you have 60,000 samples, for testing you have 10,000 samples, a very classical example. Now, if I try to train this network without adding any kind of a noise, then on my first layer, if I try to visualize these kernels, then this is what it looks like. Okay, so let us count down how many do we have: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, it means that there are 120 hidden neurons over there, and each of these is 28 cross 28, which we have. Now, these kernels which you see, these are basically convolution kernels which it has learned, and these are my first level of feature extractors. But now, a lot of these are very bland looking and very near to 0, and as if like they do not extract any particular feature. Now, that is a risk over there. Now, what happened is that if we started adding noise, which was add those perturbations to it, and say this noise is 25% of a noise parameter, which means that the maximum amplitude of the noise or the energy of the noise is 25% of the energy of the original signal. So, you can control down that factor over there. Now, once we have 25% noise added over there, you see that it has started to learn down much better representation of features, and then these bland appearing or no feature extracting ones also went out, and then you can see down exact features coming down. So, while this one is retained, this particular patch is what corresponds to this patch, and it has retained. On these 3 patches, while it was not learning anything, it did end up learning new kind of a representation over there, and that is something which is interesting to see, that newer kind of representations get learned when you add down noise over there. And to go down to make even a statement that noise is actually good, noise is good in terms of making it more robust to learn down newer kind of features which it wouldn't have learned otherwise. You cannot guarantee that you will be putting down all sorts of samples which are ever existing in the world. Your training data set is always limited, but then in order to generalize, it will have to try to figure out what are features which will describe an unseen, unforeseen object of the same class or category as well. So you see that adding a noise over here does work out that magic. And then we also try to look into dynamics of weights with noise, which is if more and more amount of noise is added, then does it go on good. So over here we consider two different neurons, neuron A and B, which appear as if almost similarly noisy, not basically capturing anything. So these values are very close to 0 when you add down a 0% noise. Now when you add a 10% noise, they start to have some sort of an appearance over there. So you would see this dark blobs coming out, but at two different regions, and they appear still to be like as if learning something similar sort of a nature. At 20% noise, they also appear to be learning similar sort of a nature, and this dark blob has grown bigger. So this is where it more of mimics an inverted Gaussian kind of a, or more of like there is a 0 value, there is some sort of a positive value, and then there is a very high negative value is what it comes down. So it's more of like a Laplacian of Gaussian which is created over there. So it's a LOG equivalent kind of thing which it's learning. But then the moment you see that you add 50% noise, while the top neuron retained its own Laplacian or Gaussian like behavior, the bottom neuron started to mimic something like a Gabor wavelet. And this is quite interesting, because you see that by adding down noise, while it's trying to generalize over a larger number of unseen examples, in order to generalize, it did end up learning newer kind of features, and that's a real interesting fact, that it will not memorize but actually learn to be even better from now on. Now from there, let's get into the other kind of an example where they try to like really put up the data in a different form of way. So these examples are basically ways in which you can change down the nature of the data and then make your training more and more robust. And so what was found out is that stacked denoising autoencoder and SDA, stacked sparse denoising autoencoder and SDA E of with 3 hidden layers over there was sort of outperforming on most of these kind of rotated versions or unforeseen versions on which it was training down for digit recognition than any of the other classical ways, including deep belief networks or even support vector machines. So that's quite an interesting observation to make from these kind of very simple learners. Now the next one which I would discuss is on OCT tissue characterization from our earlier work, and so I would not be going down any further through the details on this data set, because this is what we had done in the earlier week as well. So here if we look into, so this was the sort of network which I was dealing with. So there were just 2 hidden layers in the network, and this is what was predicted out, and then my objective was to relook into what it had learned. So you see, you remember that this is what I was showing you out as it was learning in the first hidden layer, and a lot of these weights were similar, and that should have an impact in the second so the connection between the first hidden layer to the second hidden layer in terms of it creating a lot of zeros. And this matrix, this sort of a weight matrix, so this is one weight matrix which connects down my neurons in my first hidden layer to the neurons in my second hidden layer, and this is practically a sparse matrix, because very few pixels except for 5-6 pixels over there, everything else is perfectly 0 value, and that brings it very close to it being an exactly very typical representation of a sparse autoencoder. So on the take home messages over here, what I have is that I would re-suggest you to get back into this thesis from Rasmus Buchbaum, and which has much more details if you would like to get into understanding what happens on other kinds of cost functions and other types of sparsities or any other more improvisations which you can do, and what changes you need to bring over there. As well as Pascal Vincent's JMLR paper is a very good treatise on understanding sparse denoising autoencoders. So this is what brings me an end to our understanding with very basic autoencoders, and while we are still sticking down to one single sort of a learning algorithm at itself. So in the next week we will be looking into different kind of cost functions and different kind of learning algorithms and initialization methods and how they impact down your process. And The rest of the classes we will be doing a bit more of coding based tutorials in order to get you more closer to understanding practical concepts and how to train down these networks from scratch and create down your own autoencoder networks in stacked modes in with sparsity and with denoising criteria. So, with that, stay tuned, and we will get back with more details in the subsequent classes, and thank you.